Yeah, I don't think we met, David. Yeah,
Hi, yeah, nice to meet you. So I'm I guess officially running the program right now, but I
oh,
I
you mean the center or?
the center, yeah. So I'm currently the director, but I'm particularly looking forward to this. I I just talked to a bunch of the students in my group not so long ago about reviving something that I played with a long time ago, with looking at solutions to the discrete sine Gordon equation,
Oh,
actually.
right, yeah.
And I have this long-standing interest in nonlinear eigenvalue problems and using them to do stability analysis for problems where you've got a maybe not compact perturbation that's moving around, but an operator that's basically flat plus some almost compact
Right,
perturbation, right? Because then you can capture what's going on in the far field with a boundary condition, and the boundary condition will depend on your spectral parameter differently than the PDE in the domain does. And so you get a nonlinear eigenvalue problem out of that you can
right.
use to do stability analysis. And then the perturbation theory and algorithms for that class of nonlinear eigenvalue problems has been sort of a long-standing interest and is interesting to some of the students too. So
That's actually, yeah, because I'm also interested in stability, in particular discrete sine Gordon, like a Frankel-Kantorova type models. Yeah, and I think it's a very difficult issue, especially because I don't know what kind of solutions are you interested in for that problem?
so the ones that I've actually done anything with are just the stationary kink type
Stationary,
of
yeah.
solutions. But
Because for
you know,
traveling waves, it's actually a very difficult problem because you get these kinks which radiate energy, and so you no longer have, like, unlike, for example, solitons or solitary waves. These are like not only they don't decay to zero, they also have like this oscillations, quasi-periodic oscillations that you have to deal with. So
right.
it's not, yeah, it's not an easy thing to do. We did some recent work actually on, so we did compute. Okay, so we cheated a little bit because we put some damping in. So if you put some damping, then of course the oscillations go away. Hi team. And then you can do like Floquet type analysis. At least computationally, we could compute the spectrum and see, and look at stability. So, but then to actually prove something about that that's a different story.
Yeah.
So when did you move to San Francisco?
Oh, so yeah, I just actually this room is not very good for like Zoom. First of all, like it's not very clean, and then second, there's sun, right behind me, so it's, yeah. So I figured I'll just use my background.
Okay.
And after all, I used to live there for a couple of years, so not in the Bay, but near.
Right. Was that for 2 years?
Yeah, when I was a postdoc at Stanford, remember? Yeah.
Yeah, I do, but I didn't remember it was for 2 years.
Yeah, a couple of years. Yeah. Although, I have to say I didn't really enjoy California at the time, was because it was just, my life was a complete nightmare. I had to always look for a job, or do the job, So I didn't really like appreciate California back then, and then like later I went there. I was like, it's nice actually.
I lived in Southern California for a couple of years before I got my PhD, but that's an entirely different world.
Oh yeah.
But after this election, I have to say, God bless California. Thank you. Thank you.
And Michigan and Pennsylvania.
Yeah, but California just has this massive,
Right.
block to offer.
Yeah. No,
Anyway.
yeah. Now we need Texas, right? It almost worked. Yeah. It looked like in the beginning, looked like Texas might actually. Right.
Yeah,
But then of course,
yeah.
But it's going to happen. I actually talked to someone recently, and they said like maybe not this election, but eventually Texas will turn blue.
Hmm.
So
With all the Latin people that live there.
yeah, and just I mean, it's always been like big cities, right, versus country, but
That's
now it's
right. That's true. Yeah. I mean, my home state of Missouri, right? They've taken to calling it Missouri,
oh
right?
right,
Because
yeah.
it's such a red, you know. Okay, but St. Louis, my hometown, they voted for Trump. I mean, for Biden over 61%, and that's about as good as it gets. I mean, okay, Tompkins County was 68%, but the county around New York City was 63. I mean, what more do you want?
Yeah.
There were a couple of other counties too. The one that's around the university in the Columbia area, and then around Kansas City, they voted for Biden. But the rest of the state, whoa, red, red, red. But I mean, just about every state in the union is that way. It just depends on the
Yeah,
urban versus rural populations.
it was still shocking how close it was. I mean, like, I guess we should have expected this, but still,
Yeah.
after all these years,
Yeah.
but still a lot of people voted for him. Yeah.
Uh, so Erica, what do I need to do here? Is there anything, because I have to admit I'm technologically challenged. So
So you need to do 0 for technology. We're all set. Anna has already shared her screen, so that's all set. You just need to make the in fact, Anna, I was thinking, since we had tried to host you in person last spring and this fall, I don't think I ever asked you if you mind if we record this session. Will that be all right with you?
Oh yeah, sure. I mean, it's not going to be pretty, but it's okay.
It will be beautiful, but it's already recording now, and typically, so I'm glad you said it's okay. But
oh,
typically,
we recorded all these political conversations too. Okay.
and then we'll get cut. All of that will get cut, and I will, it will go into the ether. I promise not to save it. And Tim, then you can just start. You may have noticed we've been starting at like 3:32ish.
okay.
Hi, Jim. It's so nice to see you.
So I think, Tim, do you have that little quick checklist of the announcements just about the recording and how questions can be asked, et cetera?
But am I the one who's marshaling that? That's what I'm asking.
Yes, so or it kind of depends on Anna too. Some speakers are comfortable with people just, unmuting themselves and asking whatever.
I'm good with that. Yeah, if I have to watch the chat, that will be a little distracting. I think it's better if people just unmute themselves.
Yeah, don't worry about the chat for sure. But Tim, yes, as faculty host, the idea is if you see someone that has raised their hand, they will go to the top of the list of participants or the screen, however review is set up. So they can unmute themselves if you want to announce that, or you can just call on them if you see anyone raising their hand.
Okay, sounds good. Yeah.
So so in other words, I'll be the one watching the chat room.
Oh yeah. Oh, if you could do that, that'd be great. Yeah, yeah. And then you can just tell me.
At the end, right when Anna is finished, I'll paste into the chat the link in case people don't have it handy for GatherTown. But you would just announce that. I'll be here listening in, but all the formal stuff you can announce.
Okay.
That works.
So that's some place to virtually gather afterwards if you want to.
Yeah, in lieu of a real reception. Yeah. You haven't been to Gather?
No. What's the name of it?
GatherTown.
GatherTown.
In fact, do you have that email I sent you about hosting? That stuff is all listed in order there. It might be handy to just have that up so you don't have to think about it.
You probably do, but then what do I do? Is it just a different Zoom link?
It's not Zoom. It's actually a different app. It's called GatherTown. And so I'll put it in the chat and you can just announce to people. Let's see if I can find this for you.
Okay.
I'm just going to send it so you have it right at the top of your email.
Okay.
And people will have to leave the Zoom meeting and then jump into Gather. Here's this again. And then it just gives you the housekeeping things that you announce at the beginning and then to monitor. And then item 5 is about GatherTown that you can announce after it's done.
Okay.
So this is my first such Zoom talk. I mean, except I gave something to students before. I mean, and obviously teaching, but I haven't done this. It must be a little weird.
But have you just been teaching online exclusively, or?
Yeah, yeah. I mean, there are some students who actually go. So we have this thing installed in the classrooms. So there are a couple of students of mine go to the classroom, and I appear on the big screen. You know.
We just got a message from the provost that this campus has gone on yellow alert. We've been doing so well, but I guess there was an outbreak a few days ago, and now it's saying that there are even more. So we're on yellow alert.
We have they call it postures. There's elevated risk posture, guarded risk posture. I could never understood what the difference is, but you know, they just tell us some things, and sometimes it's kind of inconsistent. I think it looks like administrators are fighting with each other whether to allow students to attend class or not, you know. So,
Right.
So it's.
So should we go ahead and get started? Erica, yes? You know, it's.
Sure. I mean, we could, it's 3:31. You could,
Right.
up to you, Jim. Sometimes we wait till 3:32. Some more people may trickle in, but
Right.
Just go for it.
We got a pretty good crowd now. So it's a great pleasure to welcome back Anna Vainchtein. She graduated from this department that used to be called Theoretical and Applied Mechanics. You're the one that confessed in your bio it was in 1998, so I'm not embarrassing you by saying that. And back in the good old days, and she's done really well for herself. You mostly been at U Pittsburgh. You had a little
That's right,
postdoc,
yeah.
and she's a full professor in the math department, and we're really proud of her. And yeah, today she's going to talk about solitary waves and non-integrable lattices. Take it away.
Thank you. It's really nice to be back, even if virtually. I was hoping for an in-person talk, but it was not to be. And I really have very fond memories of doing my PhD at Cornell and working with Tim and Phoebus, who is now gone from Cornell. So it's a pleasure to be back after some years and maybe update you on some of the stuff I've been doing together with many other people. So today's talk will be based oops, I didn't mean to do that. On joint work with Jesus Cuevas Maravak, who is at the University of Sevilla, and my student Henry Duran at Pittsburgh, Panos Kivrakidis at the University of Massachusetts at Amherst, Doug Wright and Ron Perlin, who are from Drexel, Yulia Sarasvetsky at Technion, and Lev Troskinovsky, who is now at ESPCI, and Haitao Shu at Huazhong. Let me start. So the talk is about solitary waves. So solitary waves are this localized nonlinear waves, which arise in nonlinear dispersive media in general as a result of this interplay of dispersion and nonlinearity. So and they were, of course, famously discovered in water waves. This is actually a picture which attempt of a 1995 attempt to recreate the discovery of solitons by John Scott Russell. He was riding on a horseback and saw this huge wave and then he started studying the properties of this wave, and that's how the waves were discovered. But then I should also mention that in integrable systems, the waves are usually called solitons because they behave like quasi-particles. They maintain their shape and speed after collision. And they play a huge role in many areas of science, from biophysics and optics to, of course, water waves. So here's a picture of an experimental and numerical study on a granular chain where they study how solitary wave interacts with impurities. Okay, so so the story, my talk today focuses on solitary waves in discrete media. So the story goes back to Fermi Pasta-Ulam problem. So Fermi Pasta-Ulam and Singo, who actually did the numerical simulations for this work, they looked at the chain of masses connected by nonlinear springs, which had quadratic, cubic, and piecewise linear interactions, so, I mean, nonlinearities, and they used one of the first computers called MANIAC computer to try to see what the dynamics is going to be with fixed boundary conditions and a sine wave as an initial condition. And what they expected to see was that if they initiate the system with a first harmonic, first Fourier mode, they expected to see equipartition of energy among other Fourier modes, because that's what nonlinearity is supposed to do. But instead, what they saw is something completely different. What they saw is near recurrence of the initial conditions. So initially, the energy was distributed among several harmonics, but then it almost all of it, 97% of the energy eventually returned to to almost the initial state. To the first harmonic, so they almost recovered the initial state, and this kind of recurrence actually occurred, as it turns out, repeatedly. In fact, initially their results were not quite believed, because they thought maybe they didn't run the experiments for long enough, so the simulations for long enough, and so then Tak and Menzel later. Menzel was actually also that's married Singo, that's her married name. So they did additional work with a much longer time scale, and they saw actually super recurrence of the initial state. So this kind of quasi-periodic state exists for a very long time. But equipartition does eventually emerge, as it turns out, just on much larger timescales. Right. So Zabusky and Kruskal came along 10 years later to explain this paradox that was observed in the FPU problem. And what they did is they looked at the Korteweg-de Vries equation. Actually, they looked at numerical simulation of discretized Korteweg-de Vries equation, which, as it turns out, describes the low energy limit that was studied in the FPU simulations. And this equation, which was derived back in 1895 to describe shallow water waves, has soliton solutions in this form. So so Zabusky and Kruskal, they considered a system with periodic boundary conditions and cosine initial conditions. And what they saw is that this state eventually gave rise to multiple solitons, which started, interacting with each other, via this elastic collisions, and the system periodically refocused into the initial state. So the formation of solitons explained this peculiar phenomenon that FPU observed. Now, I should say that KdV solitons, have this property that they, because the system is integrable, they have this property that they have, when they collide, it's just an elastic collision with nothing changing except for a phase shift. Away from the KdV limit, the system is typically non-integrable, and you have inelastic collisions and eventually onset of chaos. So so going back to the FPU chain, so let's actually consider the system in terms of strain variables. So we write it like this, and we look for solitary wave solutions with, so these are traveling waves with velocity v, which correspond to homoclinic trajectories of the advanced delay differential equation, which is this one, and are selected by the boundary conditions saying that the waves are localized, so that it goes to 0 at plus and minus infinity. And we rescale everything so that the sound speed in the undeformed chain is 1. And so it wasn't until 1994 that Frizik and Wattis showed that such solutions actually exist for a large class of superquadratic potentials. with as long as velocity is supersonic, so greater than 1. But even before that, in 1967, Toda actually created a lattice which is integrable. So he came up with a nonlinearity that makes the system integrable. So this particular choice. And in this case, you can construct exact soliton solution in this form. So these solutions are, in fact, so it was proved later that their solutions are, in fact, stable. Okay. But Toda and integrable systems in generally are not generic. So, for example, you cannot explain finite thermal conductivity with Toda lattice. So, so most FPU systems are actually non-integrable, and for non-integrable systems, you don't have tools that have now been developed thanks to the discovery of, FPU and Zabusky and Krushkal work. This whole machinery that was discovered for integrable systems like inverse scattering transform, that is not available for non-integrable systems. So instead, what people do understand well is the low energy limit. So so that's the KdV limit, where solitary waves have small amplitude and long wavelengths, and they are well approximated by the KdV soliton. So that was studied by EOS and Frizik and Pego in a series of papers. So this is a picture actually from Frizik and Pego. You can see the small amplitude and long wave solution of the KdV equation, which approximates the solution of the FPU system. And such waves are stable, and the energy tends to 0 as you approach this sonic speed. Now, the other limit, which is also quite well understood, is the hard sphere limit, the high energy localization limit. So this was studied by Frizik and Mattis, and later by Herman and Mattis. So here you've got, if you consider an interaction potential that has a vertical asymptote, then as you, so there are compressive solitary waves that tend to a tent-like profile, like this triangular sort of wave, when velocity goes to infinity. So these solutions correspond to one particle moving at a time. And these waves also were proven to be stable. So between these two limits, the usual approach is to compute the traveling waves numerically. So by now, some good methods have been developed, usually spectral or pseudospectral methods such as Eilbeck and Flash scheme. Or people also can obtain those solutions just via direct numerical simulations. One can also construct quasi-continuum approximations. So the idea is to approximate the discrete operator somehow and convert the advanced delay differential equation into either differential or integral differential equation. So a PDE or integral PDE. So here, let me just illustrate it on a simple example. So if you just discretize, convert the discrete traveling wave equation into Fourier space. So this is the approach of Lattice. And there are also other people who contributed to this, like Collins from Nesterenko, Rosenau, of course. So Lattice approach was to just go into Fourier space, and then you have to look at this particular quantity, which is essentially Fourier transform of discrete Laplacian over the regular Laplacian. And then approximate that by using various expansions. So for instance, if you do the Taylor expansion, then you obtain this ODE, so just ordinary differential equation. And if you do use a simple Padé approximation like this, you obtain another ODE, and this is something that was obtained from also by Collins and Rosenau. So so it turns out that these models, by design, of course, work best near the KdV limit, so long wave limit. But surprisingly, sometimes they work quite well even away from their strict validity regime. And what's important is that they sometimes, in some cases, depending on the nonlinearity, may yield very simple exact solutions that can be used to learn something about these waves, or at least initiate numerical simulations. So All right, so I'm going to now describe some work with Lev Truskinovsky, where we attempted to compute solitary waves for the case of piecewise linear interactions, or bilinear interactions. So now, this is also a nonlinear system. In fact, people forget this, but the original FPU report also included simulations for the piecewise linear case. And so here we assume that the force is linear in the two. So there's a blue and red regime, which have different slopes, 1 and alpha. Alpha we assume to be greater than 1. And there's a transition strain in between WC, where you switch from one to another. And one can show that solitary waves then will exist whenever the velocity is between 1 and square root of alpha. And they have this general form, where everything is expressed in terms of roots of the characteristic functions that are associated with this blue and red regime. So here I show the picture of these roots. And Z here is the plus or minus Z are the places where you switch from red to blue and vice versa. So let me just maybe briefly describe the idea. So how to actually find these matching coefficients. So so the idea, because it's not so simple as, for example, solving just an ordinary differential equation with piecewise linearity, right? Just glue it together, use some continuity conditions, because now we have the advanced delay terms. It's not as trivial. What you do instead is you replace nonlinearity by inhomogeneity. So I learned about this from paper of Plitzanis, and I used it also for other setups. But it turns out it's actually older than that. There's work of Lippmann, Schwinger, and Haschen and Strickman in homogenization theory that used similar ideas. So the idea is that you write your function in this form, where theta is a unit step function, a is a constant, positive constant to be determined, and h is an unknown odd shape function, which is normalized so that its integral from 0 to z is still unknown, is 1, and it's has a compact support from minus z to z. And then if you use that and make it consistent with the bilinear assumption and also with the equation, with the governing traveling wave equation, you then arrive at this convolution type Fredholm integral equation with a kernel that is known from those characteristic functions that I mentioned on the previous slide. So, so the problem then reduces to finding a non-trivial solution of this linear integral equation, which exists only if certain algebraic conditions hold for z. And so, so technically you can solve this problem using a version of Virchow method. And then once you do that, then you use this nonlinear condition that W at Z is equal to WC to find this unknown constant A, and you can recover the strain from this formula, again, with using another kernel. Okay, so here are some results. So here we show this Z variable again. That's where you reach W, the critical strain, that you switch from red to blue and vice versa, versus V, and this is the amplitude of this solution versus V. So the black curves correspond to the discrete model, and the red and the green are the quasi-continuum approximations. So the green one is the one based on Taylor expansion, and the red one on Padé expansion. So you can see that Taylor approximation generally overestimates the width of the soliton or solitary wave, but it underestimates its amplitude. While the Padé approximation does the opposite, so it overestimates them. It creates narrower but taller waves. Interestingly, you can see quite a bit of a difference in the Z variable, but not so much in the amplitude. So, all right, and then we also looked at stability of this solution. So here I plot the energy of these solutions that we computed versus V. And you can see that the energy goes to infinity at both sonic limits. So there are two sonic limits in this problem, 1 and square root of alpha, and goes to infinity in both limits. I'll explain why in a second. So there's a minimum somewhere here around 1.05 in this case. And so it turns out that solutions are stable when you are above this minimum. So when the energy increases with velocity. So these points here correspond to results of the numerical simulations. And the crosses corresponds to simulations where the wave is unstable, so that's below the minimum. So in this case, the wave just, the initial, sorry, the wave just decomposes into a dispersive linear wave. So whereas above the threshold, you have stable propagation, at least according to, these are just direct numerical simulations. So the waves, again, so the conjecture is the waves are stable for the increasing energy and unstable when the energy is decreasing with velocity. So, so it turns out that this instability that we saw near the sonic limit is actually an artifact of the bilinear interactions. Because what happens is essentially this model does not actually have a KdV limit, because as you approach the sonic limit, the waves delocalize, but they delocalize to the transition strain rather than to zero. So so the small amplitude solutions are inaccessible to them anymore. So what you get instead is that solutions approach this solution Wx is equal to Wc for all x, and so the energy tends to infinity, and that means that near this limit the energy is decreasing. Whereas in, if you consider an FPU chain with smooth convex potential, for instance, you know that solutions delocalize to zero. That was shown by Frizik and Pega, and the energy actually approaches zero as v goes to 1. So in this case, the energy instead increases near the sonic limit, and they proved that solitary waves are stable near this limit. So to see how this can be reconciled with the bilinear case, we actually looked at smooth regularization of the bilinear problem. So we looked at the case where and this is joint work with Jesus Cuevas Marava and Pansky Vikiris and Haitao Shu. So here we looked at yeah, so we looked at f, which is f 0 at 0 and has this derivative. So essentially we replace this piecewise constant derivative by this kind of smoother thing. And so what it gives us, it gives us a smoothened corner here and a slightly smaller second slope. And what you get then is, so in this case, you do actually have a regular KdV limits. In fact, what you have is that the energy is 0 at 0, a velocity, then it increases, then it reaches some maximum value, a local maximum value, and starts decreasing, reaches a minimum value and starts increasing again. So the energy is non-monotone in this case as a function of velocity. And this maximum, the velocity at which it reaches its maximum approaches the sonic limit when epsilon, which controls how close we are to the bilinear limit, goes to 0. So when epsilon goes to 0, we are converging to the bilinear limit, and then we get this, you know, grows to infinity that I mentioned earlier. But in the regularized case, you have this non-monotone behavior, and if you compute the eigenvalues for the linearized problem, then what you see is that the maximum real eigenvalue becomes positive right when the velocity is decreasing. I mean, when the energy is decreasing with velocity. And so, and remains 0. In this case, there's always a double eigenvalue at 0 otherwise. So this analysis of the linear problem suggests that the waves are stable, again, when the energy is increasing with velocity, and unstable due to this emergence of real positive eigenvalue when the energy is decreasing. And in fact, one can prove rigorously that the sign change of dHdV is sufficient for the change of stability, because what happens is that the multiplicity of that 0 eigenvalue changes at the threshold, increases at the threshold. So the waves are, okay, I should say spectrally stable, because we're only talking about linear stability here. So spectrally stable when DHTV is greater than 0, and unstable when DHTV is less than 0. Okay, so one of the methods we use to do this analysis is computing the Floquet spectrum. So one can, if one looks at these traveling wave solutions in the discrete lattice, they are actually periodic modular lattice shift, right? So they satisfy this condition. And so that means that we can linearize the governing equations about such solutions and look for Floquet multipliers, which are eigenvalues of the monodromy matrix that are associated with this map, periodic modular lattice shift, and then you and those Floquet multipliers are related to the eigenvalues that I showed you in the previous slide via, lambda is just log of mu, lambda being the eigenvalue, mu is the multiplier. And so in Hamiltonian systems, the system is stable if all the Floquet multipliers live on the unit circle, and it becomes unstable when there are Floquet multipliers that go outside the unit circle. Or equivalently, the real part of the eigenvalue is 0. Is greater than 0. So here, this instability manifests itself through the emergence of this positive real eigenvalue, or equivalently the Floquet multiplier, which is greater than 1 when you cross stability threshold, which is DHTV is equal to 0. Okay, so it turns out that a similar phenomenon can also be observed in a FPU lattice that also includes long-range interactions. So to be specific, we here include all-to-all harmonic Koch-Becker interactions. So these are interactions with harmonic interactions with moduli that are exponentially decreasing in space. And so this problem has been looked at in a series of papers by Guy Didier, Mingaleev, Flitzanis, and Mertens and collaborators. And what they found were some interesting things. In particular, they found that not only you can have an energy velocity relation which is non-monotone, like in the previous example that I showed you, but you can also have a case, depending on how you tune the parameters, where the energy velocity relation is multivariate, like in this picture. So recently we looked at, with my student Henry Duran, and also with Shuren Kivrakidis, we looked at this system more closely and computed the Floquet multipliers for it. And what we saw is, and what you can also prove in this case is that in this case stability threshold corresponds to DH/DS being equal to 0, where S now is a parameter along the the curve. So you no longer have a single valued curve, but you have a parameter that parameterizes multi-valued curve. And when DH/DS is 0, that's when you you switch from stable to unstable, vice versa. And so and the computations suggest that the waves are stable when DH/DS is greater than 0 and unstable when it's less than 0. Okay. So since we started talking about long-range interactions, let me also mention the case where you just have second neighbor interactions. In this case, you've got just again harmonic second neighbor interactions where beta is a parameter that measures their relative strengths, and beta has to be greater than -1 in order to ensure that the homogeneous deformation is stable. And in this case, the sonic speed is now square root of 1 plus beta. And so suppose you have a solitary wave that exists for given V, F of W, and beta, then its asymptotic behavior is described by this asymptotics at infinity, where K is a wave number that has a positive imaginary part to ensure decay. So we want solutions to decay at infinity. And it has to be a smallest magnitude non-zero root of this characteristic function. So here W is related to K through, I mean, omega of K is a dispersion relation. So if you, okay, so I'm meeting a lot of details here, but you can study the structure of these roots, which we did. And if you do that, then you can show that, in fact, the velocity has to be supersonic, just like in the regular FPU problem, as long as beta is greater than or equal to -1/4. But when beta is even large in magnitude, so between -1 and -1/4, then the waves have to be strictly supersonic, which means that the lower bound on the velocity must be strictly greater than the sound speed. And so that happens when the interactions are strongly competitive. And such waves always have oscillatory decay. And the other set of waves, in this regime also have oscillatory decay as long as the velocity is greater than a certain critical value. So that's something that all of this you can glimpse from just looking at the structure of these roots. Okay, so here is the picture summarizing this. So here I plot V versus beta. Here, this is the sonic speed as a function of beta. This dashed curve is the critical velocity which separates oscillatory decay from the monotone decay. Okay, so what's important here is when beta is between -1/4 and greater than minus or equal to -1/4, as you approach the sonic limit, the waves delocalize in the KdV-like manner, similar to what we discussed before. But things are different here. So in this regime, when beta is between -1 and -1/4, you instead have waves bifurcating from a short length linear wave. So if you plot the phase velocity versus the wave number, you have a local maximum, and the waves actually bifurcate from this local maximum, which corresponds to some wave number Km, positive wave number Km. This limit actually cannot be described at least by the regular KdV equation, and in fact is completely missed by standard quasi-continuum models, as we showed. So this is work with Lavchuk-Skinovsky. So here, for example, Vattis actually did study this problem back in 1996, and he completely missed this part. He did predict this part of the diagram, but he missed this part because he was relying on those quasi-continuum approximations, which in fact suggest that the waves could be subsonic. But in fact, they are not subsonic, they are strictly supersonic. And this bifurcation can be described more carefully if you write down modulation equation, which happens to be, so the leading nonlinear approximation near the bifurcation is described, has amplitude that satisfies a certain modulation equation, which is essentially a nonlinear Schrodinger equation with some high order terms. And then you get something like this. And in fact, we also did some numerical simulations, and so this approximates quite well what happens near the bifurcation point, and those solutions appear to be stable. Now, a similar phenomena was actually observed much earlier in PDEs, which described capillary gravity water waves. So for instance, fifth order KdV equation and Euler equations. Yeah, so people like Grimshaw, Achilles, Higgins, they studied this this problem. And so we learned a lot from their work. So of course, in that case, the waves bifurcated from a minimum rather than the maximum, but a lot of things are similar. Okay. So now I'm gonna talk a little bit about existence of solutions in a diatomic lattice. So far we were considering monatomic lattices, which so the masses are all the same, but now we're looking at the case where the masses alternate between heavier and lighter masses. Okay, so now we are writing solutions, equations in terms of displacement because it's more convenient this way. And epsilon here is a parameter which controls, measures the ratio. Everything is scaled, of course, and epsilon is just the ratio of the two masses. So it lives between 0 and 1. And the question is, can a solitary wave propagate through such a lattice? So in other words, do there exist solutions of this form? So now, again, I write everything in terms of displacement, but I require that the particle velocities go to 0 as c goes to plus or minus infinity. And everything depends on this traveling wave coordinate again. So on the first glance, the answer appears to be no. And in fact, people, I think, believed for a long time that the answer is no. Because if you do, so here I did some numerics with a diatomic total lattice, which by the way, is no longer integrable, right? So once you take a total lattice and you make it diatomic, you destroy integrability. Okay, so you take a diatomic total lattice and you initiate numerical simulations with some pulse, right? So very soon this pulse will develop oscillations. That's what you will see. So there will be a pulse propagating, but it will be leaking energy through these oscillations. And its amplitude is going to decrease slowly, but surely will decrease. And this is my attempt at drawing a phase plane for this solution. So this, okay, I should maybe explain. So this, again, so throughout this, the even numbered particles are the light masses, and the odd numbers are the heavy masses. And so the even ones are the ones which have more oscillatory kind of structure. The odd ones are the heavy ones. Okay, and you can obtain similar results for other, in fact, the similar results have been obtained for other systems as well, not just diatomic total lattice. So to explain this phenomenon a little bit, one can look at the linearization again. So let's linearize about the homogeneous deformation and look at the, again, these equations for heavy and light masses. And you do the usual thing, look for solutions in terms of plane waves, and you derive a dispersion relation. Now, as is well known, for a diatomic lattice, the dispersion relation has two branches. One is the so-called optical branch, and the other one is the acoustic branch. So whereas like the regular FPU chain only has an acoustic branch. And in fact, something that will become important later, the optical branch is well described by square root of 2 over epsilon when epsilon is small. So if you now, so this is omega versus k, the frequency versus k. Now, if you plot the phase velocity versus k, what you see is this. And since I already mentioned that the waves, solitary waves can be only supersonic, and this is the sound speed, the dashed line. So if you look at any velocity above the sound speed, such velocity will be, will necessarily, so the corresponding, so this velocity, the corresponding phase velocity will then be compatible with vibrations, optical vibrations at a certain frequency, right? Each of such velocities, right? So you expect to see optical vibrations at supersonic velocities. That's what I'm going to say. So, and in fact, okay, this is linear analysis, but you can prove rigorously, and that was done by Hoffman and Wright, existence of such vibrations in the nonlinear case as well. Okay, so at first glance, you see this optical vibrations which take energy away from the pulse. So the answer seems to be no. But Jayaprakash, Starosvetsky, and Vakakis back in 2011 showed that, in fact, they considered the diatomic granular chain, and they found a sequence of mass ratios at which there exists, at least up to the accuracy of numerical simulations, genuine solitary waves, so no radiation. And actually, I also found a paper by Tabata in 1986, who found a stable solitary wave in diatomic lattice, total lattice at some magic number. So the ratio had to be like this. In fact, you have to include more digits to get the precise value. So then we went and did some numerics, and so here I'm showing so we found more magic values like this for the diatomic total. So here again, the red and blue are the light masses at different values of n. These are all velocities versus t, and particle velocities versus t. And the other colors are the heavy masses.
Can I ask how you got
Yeah.
those magic? How do you get those magic numbers?
Well, okay, so we did some asymptotics, which I'm going to tell you about later, to predict the values to some extent. And then we did the numerics near those values and did some optimization to minimize the energy emitted from these waves, right?
Okay.
So by sort of doing, you know, optimizing the energy, eventually you converge to a value of epsilon where, at least to numerical precision, you have no radiation. So there's a certain anti-resonance condition that must hold in order to ensure that there's no radiation. So that's what I want to describe. So in order to get some idea about this, one can do multi-scale asymptotic analysis. So assuming that epsilon is very small, so that you have two time scales, the slow time t and the fast time tau, which is t over square root of epsilon. And so those time scales for small epsilon are well separated. You can then look for solutions in this form, so up to high order of epsilon. And then you look at the slow dynamics and the fast dynamics. So the slow dynamics is described for heavy masses just by this equation. So that's essentially what this is just the equation for, like, ignore the light masses, right? And just look at the chain of heavy masses. That's what it is. And the light masses is just the average. The displacement, the slow time displacement of the light mass is just the average of the corresponding displacements of the heavy neighbors. Okay, and then for fast dynamics, you actually end up with uncoupled oscillators, which have slowly varying natural frequency and some driving force, which comes from negative acceleration of the light masses. Of slow negative acceleration of the slow dynamics of the light masses, to be precise. Okay, now, but the epsilon equal to 0 problem is essentially like a monatomic lattice, right? And for monatomic lattice, under certain conditions in the potential, we know there exist solitary wave solutions. So that was proven by Frizzike and Wattis back when they were graduate students, by the way, at Edinburgh, you know. They proved this remarkable result, 1994. So, so using that, we can actually assume that there exists for epsilon equal to 0 a solitary wave solution, right? Which describes. So from there, we can figure out you know, those parameters that I mentioned, the frequency, the slow varying frequency, and the forcing, look at this equation. So essentially, to understand the fast dynamics, it's enough to just look at this equation, where we can always select, since this solitary wave is defined up to translation, we can always you know, use its properties to select the solution that gives us even omega and omega 0 and odd f0. And then we look for solutions of this uncoupled oscillator satisfying that goes to 0 as t goes to minus infinity. And one can show that such solutions will develop oscillations of frequency that I mentioned earlier already, omega equal to square root of 2 over epsilon, at large times, unless this condition holds. So this is a Fredholm orthogonality condition that basically ensures that the slow motion of the center of mass of the two neighboring heavy masses does not excite any fast oscillations of the lighter mass in between. So that's anti-resonance. And here Y2 is a solution of the homogeneous problem that is odd. So because F0 is odd, so this one is also odd. Okay, so for diatomic total lattice, you can carry out this program almost completely. What I mean by that is we know the equations, we know the exact solution. Here it is. We can figure out the slow dynamics of the heavy and light masses. And the homogeneous oscillator equation is this equation, which if you studied quantum mechanics should be familiar, because this equation is essentially a one-dimensional time-independent Schrodinger equation for the sec-squared Poiseuille-Taylor potential, and you can find you know, many classical books like Landau and Lifshitz and Floquet, which I prefer because it has like a lot of nice asymptotics and other papers and books. So so in fact, yeah, if you look in the book by Floquet, you can find even an odd solutions of the homogeneous problem in terms of hypergeometric functions. So it doesn't look pretty, but it's exact. So and then he gives you some asymptotics. Yeah, so the behavior of the asymptotic behavior of the non-homogeneous solution of the non-homogeneous problem is like this. So where you know, I guess there are all these gamma functions entering interplay, but the bottom line is that if you want the oscillations to be gone, then you have to set this to be equal to 0. So this integral must be equal to 0, and in this case, you can actually compute it. Well, in fact, for this, there's this parameter nu that enters the picture. Nu is, let's see, nu is related to epsilon. So if nu is integer, you can actually compute this explicitly using residue calculus. Otherwise, you do have to do some numerical integration, but it's not. It's pretty easy because again, you know what these functions are. So, and you know, they're well behaved and so forth. So anyway, so this function here is, it's plotted versus epsilon, and you can find its zeros, and those zeros, at least according to the asymptotic analysis, correspond to those so-called magic values, the spatial values. Yeah, here's some results. So these are the anti-resonance values in asymptotics. And the corresponding light mass velocity pulses that one can compute. Okay, so we can't really trust these results. These are, you know, way outside the validity of our assumption of scale separation. So we kind of forget about those. But the other ones actually are pretty close to the numerical results. So if you compare, this table compares to the numerical values we obtained, you can see that they're pretty close and get closer as epsilon gets smaller. So, so the conjecture is that there's a countable infinity of mass ratios that accumulates to 0 and depends weakly on kappa. Kappa being the parameter that controls the speed of the wave, for which there exist solitary wave solutions, genuine solitary wave solutions. Okay, so of course, those solutions are not generic at all, right? I mean, they all cannot, you have to tune the lattice just so to get those waves. So so one calls such waves embedded. There's in physics they say embedded solitons, right? So they, in this case, they're embedded in a more general class of traveling waves, which are known as weakly non-local traveling waves, and usually called nonoptera. So actually Boyd was, so such waves were actually observed, I should maybe state now, they are discrete analogs of waves that are known to exist in capillary gravity water waves again. Boyd, for instance, coined this term nanoptera. And nanopteron is a pulse with very small wings. So small pteron wing, right? Nanoptera. So those nanoptera are known to exist in this PD context, but they also exist in the discrete lattices. And so here I'm plotting something that we computed for recently for the two variables are the strain in, so W here is the strain in the chain of heavy masses, and Z is something that measures the deviation of the displacement of the light mass from its from the average of a displacement of its heavy neighbors. And the reason I chose those two parameters, those two values, is because one is even and the other one is odd. So this one is so they're actually oscillations on both sides. I just plot on the part only the right part, and here the same thing. So so those are waves which have which do not decay to 0, but rather continue to oscillate. So this is for diatomic tode for some specific mass ratio, which is not one of those magic values. So we computed this recently, or so I actually spent most of the summer working on this. But recently I found out that Favre and Hupkes also computed those waves using a different approach. while I was working on this. So independently and using different method, but still. Now, rigorous results also exist. So Hoffman and Wright proved that such waves exist for diatomic lattices when epsilon is very small. For epsilon, for the mass ratio, which is near 1, so Favre and Hupkes proved existence, and they called those waves micropterons because in this case the oscillations are not that small. Also Favre and Wright proved the existence of such solutions in the KdV limit. Or near the KdV limit, I should say. So, and I also should mention the work of Lustre and Porter and Lustre, who did some exponential asymptotic analysis on this type of solutions. And like I said, these were early observed for capillary gravity water waves, and there's work by Hunter Shirley and Pamo and collaborators describing them in much more detail. And Boyd has done a lot of numerical computations as well. And Grimshaw also contributed to that. Okay, so I think it's time for me to conclude. So, I tried to give you just a taste of the type of problems that I'm interested in, and what the type of things that has been done over the years. And of course, there's a lot more. So I should say that 65 years after publication of FPU report in 1955, there has been a lot of work on this type of nonlinear waves, and not just solitary waves, but also things like breathers and kinks and dispersive shocks. There are many, many interesting phenomena that still are not fully understood or far from it, and so this remains a very active area of research in nonlinear science. For the stuff that I've talked about, solitary waves and also weakly non-local lattice waves, many open problems remain. So, for instance, I discussed a little bit stability, right? Stability conditions. Their stability theory has not been nearly as developed for this as, for example, in continuum theory, right? So something like Grylakis, Schatten, Strauss results, nothing like this. So we know we have some partial results, but for instance, even like what I mentioned to you, that the energy increasing. So under what condition is this energy-based criterion sufficient for stability or for instability? That's not clear yet. So there's no rigorous result showing that the waves are stable when the HDV is greater than 0 and unstable when the HDV is less than 0. What is known is that stability will change when it changes sign. In 2 dimensions, it's pretty much a lot of open field. I mean, there are obviously a lot of results here and there, but there's no general, as far as I know, it's the theory for existence, understanding of all the properties and stability for sure in 2 dimensions. For this embedded solitary waves that I mentioned in the second part of my talk, there's no rigorous proof that I'm aware of existence of such solutions. There's the proofs of existence of nonoptera, but even those proofs cannot actually show that, in fact, those solutions will exist at those particular values, at some special values of mass ratios in diatomic chains. And now actually some of the recent work that we've been trying to do is to understand stability of this embedded solitary waves and nonoptera. So that's also an open question. So here I'm just listing some references, things that I mentioned. There's more stuff on my website, and thank you very much for your attention.
So let's unmute and thank the speaker first of all. We have plenty of time for questions. I'll ask a question or two.
Sure.
Can you go back to the previous slide?
Mm-hmm.
So where you were talking about the capillary gravity water wave models, should we view your models as some kind of discrete analog of that, or is the solution?
Not exactly, no, not for this one. So the literature there is mostly, I think, on 5th order KdV equation, right? So which is not exactly the same thing as here. So for instance, there's only one variable there. Here we have two this is that in diatomic lattice, you necessarily have to work with two variables. But there are some techniques that can be carried over. For instance, I know that Hoffman and Wright have this I don't know 50-page paper where they prove existence, and they do use some techniques. Oh, I should have mentioned there's also work by, see, because of Zoom I cannot see part of my slide, but there's this work by Beal, where he proved existence of for the PDEs, problems like capillary gravity water waves, and so they do use some of his techniques, but not everything goes through. So there are certain things in the continuum that doesn't translate into the discrete realm.
And did you just say there's nothing like this for two-dimensional lattices?
You mean this or Nanoptera?
Yes.
No, I'm not sure actually. There might be. No, there are definitely solitary waves and some examples of solitary waves in 2D. I think what is true though is there's no general like rigorous results. I mean, I'm not aware of any rigorous results for existence or stability, or even yeah, and in fact. Yeah, I mean, like you can easily construct, for example, planar solitary waves, right?
Yeah.
So that's not a problem. Or like consider, I don't know, and anti-plane shear or something, and you can do that. Yeah, that's for sure. So it's not so it's not. I'm not questioning that they do exist, but I expect that there will be much more interesting things to see in terms of stability, right? Because you can have this different types of perturbations. Like it's known, for example, that in continuum realm that what is it? Kadomtsov Petrashvili waves are unstable to certain types of perturbations, right? So something like this could be also true in the discrete lattice. I would expect that, but probably more stuff as well.
Any other questions out there? Everything's clear? Okay, well, if that's the case, then we're now inviting you all to go to gather.town, and there is, if you go on the chat, there's the address, to click on, and it's in lieu of having a little reception afterwards. So let's thank the speaker again.
Thank you very much.
Thank you.